Okay, so welcome to the last tutorial of the day. It's going to be a two-parter because wonderfully oversubscribed this year in tutorials, which is great because I'm the tutorial chair next year, so hopefully there will be the same level of enthusiasm then. So the general theme of this last session is time. I'm going to be talking about temporal planning. Luke's going to be talking about time in simple temporal networks and the way to work there. The title for this is actually because it marks 10 years since the journal paper on PDDL 2.1 was published. And this was the first standardized version of PDDL which actually featured a temporal action semantics. So I'm going to be talking about the extension of that, and specifically I'm going to be focusing on this little area in the middle. Really this boundary here between what we think of as being classical planning, how it meets temporal planning, and what really are the challenges which lie on this frontier between, well, we're doing planning, but what is it which actually characterises it as being interestingly different to just straightforward classical planning research. So really I'm going to be talking about the action representation to give you sort of the basis of what we're working with. I'm going to be focusing on one approach, forward state space search for reasons of time, how we manage the temporal constraints we get when we do temporal planning, and various other challenges which we encounter along the way. I'm not going to be talking about most of temporal planning, as you might guess. I've got 45 minutes, maybe an hour, so I'm only going to look at PDDL 2.1. I'm not going to be talking about timeline approaches. I'm not going to be talking about the raft of temporal planning work that predates 2003. There's lots of good literature out there. I'm just focusing on this one part of the elephant today. I'm only going to be looking at forward states versus space search, so I'm not going to be talking about some of the most competitive temporal planning approaches out there. I'm only going to look at propositional planning. If you want to hear about numbers, then this morning's tutorial was great if you didn't see it. Otherwise, there's a workshop tomorrow on planning in continuous domains. It's well worth going. There's lots of exciting work in temporal planning, looking at where time meets numbers, things like continuous processes and so on. Okay. Well, the first question is, if we're going to do planning with time, well, what do we actually mean by time? The most basic unit that we could work with is an action. So what are our actions going to look like? Well, in the non-temporal case, you can imagine an action might look like this. It has some preconditions, and if we apply it, we get some effects, we update the world. So maybe, well, let's just make the action slightly fat. Let's just add a time dimension to it, and say, well, we've got some preconditions, and then maybe these have to hold throughout, and then at the end you get some effects. And, you know, that is a model of time. We could have a temporal planning semantics which look like that. The issue with that semantics though is, well, what you could do is squish it back in again, and then you could just pass it to FF, and FF would give you a non-temporal plan, and then you go back over it and you put the action durations back on. So it's not actually increased the theoretical complexity of the language. We're not concerned so much about the execution time of the plan, perhaps. It would just stay with this basic model. We have some preconditions. If you meet those, you get some effects. Then we've not actually pushed sort of the technical complexity of doing temporal planning. So what should we do a bit differently? Well, in PDDL 2.1, the language which was chosen by Fox and Long was essentially based on this idea, well, if we're starting an action, then in a sense we have made a decision at that point, being the term happening. So we have a happening which represents when we have chosen to start an action, and then we have a happening of when the action has finished. So what we could have, for various reasons, because it's an elegant way of letting this model various things, is to allow preconditions and effects to be attached to both the start and the end of the action. So instead of just having preconditions at the start and effects at the end, we can now mix and match. We can have effects at the start too. And we can also separate these notions about what preconditions we insist have to hold during the action and which ones have to hold at just either end. So I'm going to have a couple of examples so you'll see how this comes into play. To use the technical terms of PDDL 2.1, these are referred to as the at-end preconditions and effects. The invariants, if you're familiar with that terminology, are the overall conditions in the middle, and we have the at-start preconditions and effects at the start there. So I've allowed myself two slides of PDDL. It's not the nicest syntax to look at, but I couldn't do a tutorial on PDDL without showing you some PDDL. This is a non-temporal action. Hopefully you should all have seen something like this before. We want to load a package onto a truck. The truck has to be at some location. The object has to be at that location. And if we apply this action, then the object isn't at that location and it's in the truck. So that's non-temporal. If I fill in the gaps, this becomes a temporal action. So it's essentially the same fundamental structure, but we're now labelling it with these temporal annotations. So over all this action, we require the truck to be at the location. And at the start, we require the object to be at the location. Why is it only at the start? Well, immediately, we say that object is not at the location anymore. So, and it's not actually until the end of the action that the object is in the truck. So these 2 points, when the object leaves the location and arrives in the truck, they're separated by the duration of the action, which in this case is 2 seconds. To give a slightly more informative example of the things you can do with PDDL, we have an action here which only requires the person to be there to open the barrier at the start of the action. So whereas in the example, we require the truck to be there over the entire time, with PDDL semantics, you can have preconditions which are just have to happen at one point. So in this instance, the person can open the barrier, they just need to be there to start to press the button, then they can walk away. So there's actually no conditions during the execution of that. At the start of the action, we have the condition, we now get the fact that the door is open, and at the end, that fact is deleted again. So you can see we can actually have effects which look like they're conflicting, but it's really okay because that happens at the start and that happens at the end. And I will come back to this later on as an example of some of the headaches we get working with temporal planning because we actually allow you to do interesting things at the start and at the end of actions. So let's say we actually wanted to plan with these. So the question is, how far can we push a classical planner before we actually hit a wall and say, okay, we've honed in on what the interesting difference is between a classical planner and a temporal planner. So one of the first pieces of work looking at how we could exploit classical planning-like ideas to do temporal planning was a paper by Fox and Long in ICAPS 2003, which was looking at using a graph plan style approach to do temporal planning. So it was based on timestamp layers, and the key thing they did was this observation that we could have a PDDL 2.1 temporal action, and we can actually split it into several parts. So we can have a start action over here, with that start symbol there, which has some preconditions in effect. So those are the ones which were at start. We have this overall action in the middle, which just has some conditions, it doesn't have any effects. And we have this end action here. Now, just for now, I'm just going to focus on the start and the end of these. And what you can do with these, if you want to start to say, well, can we shoehorn this into a classical planning approach? If we just have a few glue facts just to bind things together, we can take the start of the action and get the extra effect AS. So A has started, A is currently running. And we can make that a precondition of the end of the action. So AS union whatever preconditions it had before. We get this extra effect, we delete that AS is now executing. So by doing this, we didn't have that fact. You'd be able to apply the end of the action without having already started it. So you can put that in and you can preserve this link between you need to start an action before you can end it, and when you end it, you delete this fact to say it's no longer executing. So, well, we could then feed this into FF or your favourite non-temporal planner, and we could get a plan which looks something like this. Start action A, start action B, which gives us a stack F, which is a precondition of ending action A, and ending action A gives us our goal G. So that on the face of it looks like a plan. Problem number 1. What if the end of action B would interfere with this goal? Now, in classical planning, if we stopped at this point, it would be fine. But in temporal planning, we've started an action. When an action started, at some point in the future, it has to finish. So we might have this action over here, so the end of B, which is just going to delete our goal fact. So to prevent this, in the PDDL 2.1 semantics, there's a simple rule: no actions can be executing in the goal state. you might think it's slightly overzealous, but essentially it protects the goal condition because it's saying anything which could happen in the future, which could violate the goal, we forbid that by insisting that we've finished all actions, so we have no obligations to anything that happens in the future. We can actually still capture this with a classical planning, so there's not a great deal new here, and if you haven't guessed already, we can add an extra goal to the problem saying not AS, not BS, not CS. So for each ground action ABC, we can have an extra goal which says not AS. So this not fact here, essentially this fact which is deleted by the action ending, we insist that no such facts are true in the goal state, so we've ended all actions in the goal state. So you can do that in the classical planner, and then that would force it to have to insert this extra action in, and then obviously come up with a slightly different plan, because it couldn't stop there anymore because it would violate the goal. If you're implementing a temporal planner, you can make this sort of thing implicit. You just say the goal formula is, well, a goal state is a goal which satisfies the goal formula and which has no executing actions. So you can build that into the planner, but there's not really an extra piece of exclusivity. Well, the second challenge related to temporal planning comes back to these overall conditions, which I'll just put to one side for a moment. In LPGP, it was a layered graph plan style approach where they had these invariant actions in the middle, and they said if we have a layer where we have started A and we haven't finished A, then at every layer between those 2 points, we apply this invariant action. And because that invariant action has those conditions, then in graph plan it forces a mutex with anything which might violate those conditions. Now we're not doing graph plan style planning, at least in this talk, we're doing forward chaining planning. Is there a way we can capture that invariant information, those overall conditions? Can we embed that into the problem in such a way that we can still actually deal with that with a classical planning? Well actually yes we can, it's not too hard. We have this fact AS here, which is true if and only if the action A is currently executing. So if we took every action in the domain and gave an extra precondition, imply AS, the invariant in A, then that would say if we're in a state where A is executing, the invariant on A has to hold in order for us to be able to apply this action. So even actions which aren't anything to do with A would essentially get this extra baggage of having to check that the condition of A could be held. Now, if A wasn't executing, then ex falso collivet, we wouldn't care what the value of inv A is. We only care that this is true if AS is true. The effect of doing this would be if we apply an action which takes us to a state in which the invariant A wasn't true and A is executing, then we reach a dead end. And the reason it's a dead end is, well, we can't apply any actions because they all have this extra precondition, and we have this requirement from the previous slide that in a goal state all actions are finished executing. So you definitely have loops running, so you can't finish there, but you definitely can't apply anything because we've put these extra preconditions. Now this is messy. This is going to put a lot of extra preconditions on every single action, one for each ground action in the domain. You can maybe use a divided predicate, it might be a nicer way of doing that. Or you can write a temporal planner and essentially do this bookkeeping built in. So at every state, you check that the invariants of the actions that are currently executing are true. But again, it's not any extra complexity above writing a classical planner. So challenge number 3. Well, I've checked that the actions are finished in goal states, and I've checked that the invariants are being respected. So on the face of it, that might be a plan. But where have the durations gone? Or more generally, where have the temporal constraints gone? We're doing temporal planning. It's slightly peculiar that we completely dispense with time. Well, let's have a look. I'm just going to separate these two out to make my life slightly simple. Now the first thing is we have a sequential plan. We're doing forward chaining planning. I'm assuming for today that we get a sequential plan. So we can say these steps come one after the other. The arrows are big. I'll draw them backwards for reasons that will become apparent during the talk, but you can read this as action B comes after action A. By how much does it come after action A? Well, we have this slightly fiddly thing, which is the bane of my life in the PDDL semantics called epsilon, which insists that after you apply some action, then its effects do not become available to be used, for instance, to satisfy the precondition of the next action for time epsilon. So when you do sequential planning, so not temporal planning, you're just doing sequential classical planning, you can just say everything is separated by epsilon, and those are our sequential plan steps. So let's inherit that for now. Let's suppose we're doing forward chaining search. We can keep these epsilon constraints in and insist that our steps are strictly, totally ordered one after the other. So that's everything we got from classical planning. Now we're doing temporal planning. Well, we also have these extra constraints that represent the durations of the actions. So say action A has a duration of 3, then we would have a pair of edges in this representation here, which would say the maximum amount of time that can elapse between here and here is 3 time units, and then working backwards, the minimum amount of time that can elapse between there and there is 3 time units. And we do a similar thing for B, so B has a duration of 5.
I think assuming that the duration of actions fits the...
I'm assuming it for the purpose of this slide, but in PDDL it isn't. So I'll come back to that in a couple of slides' time. So we can put the durations in, and then the question is, can we find an assignment of timestamps to this that allow us to turn this from essentially a sequential classical plan with some durations drawn on it into a temporal plan? Well, in this case, it's quite easy. If we suppose that we started A at time 0, then we say, well, we start A at time 0, the maximum amount of time that can pass between the start and the end of A is 3 time units. So time 0 is like A, and it's going to take 3 time units. I'm going to call epsilon 0.01, just so I can write out some whole numbers. And we can say that because B starts epsilon after A does, well, it's not going to start at time 0, or put it at time epsilon, and then its duration is going to be 5, so the distance between the start and end of it is going to be 5 time units. So in this case, it was quite easy. You can imagine we could take a classical plan, and we could easily go through and just write these durations on, and essentially sequence one action after the other. If we had some action C here, then we could just sort of roll forwards and build the durations and timestamps as we go. But let's reorder the actions a little bit. Now we've got essentially the same temporal constraints as before. We have our epsilons, and we have our duration constraints. The problem is now, if we look at what it's saying at an intuitive level, it's saying we have an action A with a duration of 3, and the sequence within that, we're going to start an action B, and we're going to end an action B, and B has a duration of 5. 5 cannot occur within 3 time units. So in fact, in this case, no satisfying central timestamp exists. It is impossible to say, here's a time at which we can schedule the start and the end of these actions such that we have an executable plan. So this is really the key barrier between classical planning, pure classical planning approaches, and temporal planning, is that a logically sound plan, one which meets the preconditions, one which reaches the goal, even one which meets the invariants, is not a temporally sound plan, because of these extra constraints that we have to reason with. The killer is essentially these forwards maximum duration constraints. If you don't have any maximum duration constraints, then you don't have any problem. You might have to push things a bit later than 1 epsilon, 2 epsilon, 3 epsilon. But it's the maximum duration, the forward edges with a positive weight on, which you don't have in non-temporal planning. So option 1 to how do we deal with these temporal constraints is to actually try and simplify the way of it and try and reduce it to something which is more like classical planning, not quite classical planning, but just sort of an evolution of the idea. And you can imagine if we now search with state still and put a timestamp on each state, and to avoid this issue of choosing to end actions in the wrong order, so the only difference between here and here, we're swapping whether we're going to end A first or ending B first, so we can get rid of that problem if we use a priority queue. And this approach has been taken from various planners, from SARPA to PFD more recently, and various Patrick's planners as well. And essentially, when we're doing our forward chaining search, then we get this state S, and at some time t, and we have a priority queue, either we start a new action, which would go at time t, and we would insert the corresponding end of that action into our priority queue, and we're going to put it into the queue at time t plus the duration of the action. So that's another place where it's a simplification because it assumes that the duration of the action is fixed, which isn't necessarily the case. And we wind forwards the amount of time that it's elapsed in the state, so s prime of t is f of t plus epsilon. So not strictly not all the approaches which take this general idea always wind forward by epsilon, but it's a reasonable approximation. The other thing we can do is to take the next end action out of the priority queue, wind forwards time to that point, apply the end of the action, and then increment time by epsilon so that we can then have its effect in the next state. So we have a special case for starting an action, we put its end in the queue, or we can take the next thing out of the queue. So if we run through our example, so we're going to start A, it's going to go at time 0 because that's the time of the state, and we put the end of it into the queue with time 3 because 0 plus 3, its duration gives us t equals 3. So this is a priority queue sorted by time in ascending order. Apply the action B, well it's going to go at time epsilon, and the end of B is going to go in the queue at time 5 plus epsilon, so 5.01 in that case. Then we could either start another action, or we could pick something out of the queue there, and the only thing we can do is to choose the end A there, because A comes before B in the queue. So essentially this approach eliminates the temporally inconsistent option of trying to fit the execution of B within the execution of A. So it's dealt with that problem admirably. The key thing it requires us to be able to do though is to say, when we start an action, first, when's that action going to occur? So it occurs now. And second, when is that action going to end? So it assumes that we can put this figure in the priority queue of 3 or 5.01. It assumes we know that at the point when we're starting the action. Well, is this a reasonable assumption? So coming back to my little example from earlier on, say D is going to be the action which represents opening the barrier. So we open the barrier, we get some time to queue, which is a precondition for being able to end this action C, which might be something like a truck making a journey. The barrier has to be open so it can pull into the yard at the end of the journey. To denote the fact that the barrier is open, we have this back queue, and you can see the barrier goes down when action D is finished, so we have the effect not queue. If we wanted to draw something like a Gantt chart, we wouldn't have a problem with that. We would just say, this is the action C, the truck has to make its long journey through the depot. Just before it gets there, we would start action D, and just after it's gone through the gate, we could then end the action D again. So it wouldn't matter if it was going to take the truck 10 minutes to get there, and the gate would only be open for 1 minute once the person operating it had pressed the button and then walked away. We could do that. Can we do it with decision epoch planning though? Well, let's run through the example. We're going to start action C, we're going to start driving the truck. That's going to go at time 0, because that's the time at which we're starting. And we will queue the end of it with time 10, so the current time plus the duration of the action. The next thing we need to do in our plan, let's get back to the Gantt chart, the next thing we need to do, we've done this bit, the next thing we need to do is open the barrier. So let's apply that. The problem is that has to go now, at time 0.01, and then the end of it will go in the queue at time 1.01, because these only got very short duration. And then, because of the priority queue and the rule that you can only choose the action with the shortest time out of the priority queue, in fact, we can't do what we want to do. What we want to do is be able to finish C and then finish D, but in fact, because D is queued to come first, all we can do is finish D, which means the barrier is going up, and then it's going back down again, and then the truck's arriving. But the problem is the truck requires queue as an end condition, so we'd have to lift the barrier up and down, up and down, up and down 10 times just to pad out the time, just to waste enough time between the truck setting off and the truck getting to the depot. So at worst, it's horribly inefficient. So at best it's horribly inefficient. At worst, we might have this rule which says if you only open the barrier once for security reasons, so D would delete some fact at the start, so we might have some fact F there, and then have not F there, and have no way of getting F back. If that was the case, then search would be incomplete. And in Cushing's ICAPS paper, there's a whole selection of example cases where search, relying on this decision epoch idea of fixing timestamps, is incomplete. So how do we deal with this issue? Well, the alternative option to using the decision epoch approach is to proceed on to what's kind of the theme of this tutorial, is to look at our friend the simple temporal problem. All of our constraints, well, we have two classes of constraints. They're either sequence constraints. So epsilon amount of time elapses between step I and step I plus 1. In other words, ti plus 1 minus ti is greater than or equal to epsilon. So some time elapses. And we also have the duration constraints. These are our extra headache that we have above classical planning, and this is where the variable durations come in. So the duration of A is between some lower bound and some upper bound, and this bit in the middle can be simply read as the time at which it ends minus the time at which it starts. So for each pair of starts and ends of each action, we have a duration constraint that restricts how long this can take. In this talk today, I'm just going to assume these are constant valued. In more general, if you're doing planning with numbers, then these durations can be computed at the state in which the action is applied. So they don't necessarily have to be fixed in the domain. More generally, we can see both of these are in the form some lower bound is less than or equal to the time between elapsing between a pair of points is less than or equal to some upper bound, which is precisely the form of a simple temporal problem, which goes back to a nice piece of work in 1991 in AIJ. So from a planning point of view, STPs are wonderful. We can take it and we can use it to solve all the headaches we have with temporal planning and managing the extra constraints we have to deal with. And even better, we can solve these things in polynomial time. The only bad thing is, in planning, we need to solve one of these at every single state. So every time you make a decision, perhaps not every time, but most of the time when we make a decision, we need to check, was that decision actually temporally consistent? Because what we can't do is get to the goal and then check that the STP can be used to find timestamps for the action, because by that point we may have made some really terrible decisions temporally. So typically, at least the current plan is to check at every single state that the STP of the plan so far, the plan to reach that state, is feasible. So what does a STP look like? Well, it looks like that. How do we solve them? Well, there's a neat reduction from a simple temporal problem into a simple temporal network. So each STP, which has inequalities of this form, we can build an equivalent diagram. So we have one vertex in the diagram for each time point. So in our case, these are plan steps. In the general case, we don't have to be plan steps. We also have a time zero, so nothing can come before time zero. I haven't shown them so far, but they are there in the background. And then we can turn this inequality into a pair of edges. So if j has to come at least LB time units after I, then we would have an edge in the diagram from j to I would await minus LB. And if the maximum separation, so if j can come at most UB time units after step I, then we have an edge from I to j with weight UB. So these numbers become the edge weights. So this slightly cryptic representation, which I've been using all along, is exactly the simple temporal network representation of the temporal constraints on this little example here. You can see time zero just affected on the end there. I tend to leave those out because most of the time we put the first action in time zero. There's no great reason to do otherwise. And you can see we've got these maximum and minimum separation constraints here, which correspond to the durations of the action. If the duration of the action was different, say A could be between 1 and 3 time units, and that would be at -1, and that would still be a +3 there. And the beauty of it, from the point of view of temporal planning, is not only can we use it to find out what timestamps to give the actions, such that temporal constraints are satisfied. We can also use it to do a consistency check. So if we solve the shortest path problem of a simple temporal network, when we got our timestamps, if we solve it and we find a negative cycle, then we've actually shown that the plan sequence decisions we have made are temporally inconsistent. So a negative cycle is, as the name suggests, it's a path which goes from one node back to that node, and the overall length of it is negative. So we have one here. So A starting to the end of A has a maximum duration of 3, but then we can work backwards here. Because we have this action B inside it, which has a duration of 5, we can go plus 3 minus epsilon minus 5 minus epsilon, and that gives us a path length of about minus 2 and a few epsilons from A back to itself. So if we want to check the consistency of a temporal network, and we can find a negative cycle, then in planning we can simply say that option is infeasible, we can disregard that and not have to consider it any further. So from an efficiency point of view, we can even do this before we evaluate the heuristic of the state. It tends to, there are overheads in obviously building the SDM and checking the feasibility, but this tends to be cheaper than actually, for instance, evaluating an RPG heuristic. And I should add that this works in forward planning, and it also works in partial order planning. So the plan VH is a temporal partial order planner. Again, it uses this idea of using a simple temporal network to find timestamps of the actions for temporal plan, and also to check temporal consistency as we go along. So what does that look like in search? Well, this is search taken from the planner Crikey 3, which I developed with Foxamon and Smith, who's now Coles, in 2008. What we do, as we were doing classical planning, we expand the state, we generate a number of successors. The extra step now is that we need to check that these are temporally consistent. And if they're not, we prune them. Now, the actions to start with, they tend to be okay, because if there's only one node in an STM, there's not a lot that can be made inconsistent. But what tends to happen is, as you go deeper and deeper down the plan, you start building different options. So this is the plan that starts A and starts B, just starts A, starts B, ends B, and so on. We evaluate the different options as we go along. So this starts A, starts B, ends B, and then ends A. Well, that's our little running example that I've had all along. And you can see that if we build the STM to that, it looks like this, and we have that massive negative cycle there. So we would simply throw that option out. So we would prune that statement with search space on the basis that it's temporally inconsistent. Whereas this ABAB option, which essentially looks like that, we don't have any problem with that because the 5 is no longer inside the 3 in this little example. So that's the one we would keep. So that's more or less what you need to do to push this forward-chaining classical planning search approach into doing temporal planning. You couple it with the SDN as a tool for checking the temporal constraints. Now this kind of leads me on to my next point. Show of hands, who in this room has written a forward-chaining classical planner or worked with fast downward or FF or something like that? Okay, look, that's good. So one of the things you do in classical planning, forward-chaining classical planning, is this thing called state memorization, where if you reach a state with the same facts as a state you've already seen, you can prune it because you've already considered that option before. If you're doing cost minimization, you might have to go a bit further to say, if I see a state I've seen before, and now it has the same or worse cost, then I can disregard it. Unfortunately, in temporal planning, state memorization is a real headache, because we can have states that have the same facts in, but actually are interestingly different. The facts don't tell us everything. The facts tell us what we have shown, and if we're using something like the LPGP compilation, they might tell us what actions they're executing. But they don't tell us what the temporal constraints are. So we can't just look at the facts, we have to look at the plan steps too. And even worse, we can't even say, well, the same steps in the plan, the actual order of the steps in the plan. The only difference between this option here, which is invalid, and that option there, which is valid, is the order of those steps. Assuming there's nothing which interact between B and A in this case, we could even get exactly the same facts out of that, these two sequences of actions. The only difference is the permutation. We get to a state where some facts are true and no actions are currently executed. So, if anyone actually has any bright ideas, this is one of the great unsolved challenges in temporal planning, which is fairly hideous things, and it doesn't always scale very well. But it's an interesting observation that because we have this reliance of the temporal constraints are kind of pushed to one side and solved with temporal network solver, we don't have enough logical information to really tell us what matters about the permutations of the actions we've started and ended in the plan. So heuristic guidance is thankfully something which we are a little better at. And essentially there are three options. There's the good old option of pretend we're not doing temporal planning, put an off-the-shelf non-temporal heuristic and use it. So early versions of the plan are Crikey, took FF's RPG heuristic, just found the RPG heuristic value using snap actions, so using the LPGP start and end actions. So that's a sort of zero modification. You keep the glue fact to fact AS, but say you can't end an action unless you started it, but you can use any other non-temporal heuristic as you like. So that's option one. Option two is to actually try and come up with some sort of temporal heuristic, so SARPA and Crikey 3 and various other planners, and use a temporal reachability analysis based on this relaxed planning graph where your layers have timestamps. So instead of the layers being offset by some nominal amount to say the actions in this layer, add some facts, which can be used as preconditions for actions in the next layer, and so on. We actually would say that an action here, which starts, well, we delay the end of that action until some lower bound of the duration of it in the future, so we don't get its effect straight away. And the general idea comes back to temporal graph plans, temporal planning graph from 1999. SARPA builds directly on that, and Crikey 3 that builds on that to include the start and end actions, so you preserve completeness there. Option 3 is to approximate time as action costs and then use a non-temporal heuristic. So in TFD, we make an inadmissible approximation by saying that the cost of an action in our non-temporal heuristic is going to be whatever its duration was in our temporal problem that we're solving. It's not admissible, but it's quite informative, and it's a decent heuristic. Patrick Haslam had a little workshop paper in ICAPS 2009, where he came up with an admissible heuristic for temporal planning. So it's an admissible estimate of the make span of the plan, and that was based on bounded concurrency. So you set the cost of the action to its duration, divided by the maximum number of actions you have in parallel. Because essentially the difference between time and cost is in time, if you spend €10 in parallel with each other, that's only cost you €10. Whereas the cost, if you spend €10 in parallel with each other, that's cost you €20. So by finding bounded concurrency, you're essentially dividing by the maximum amount of overlap, so the maximum overestimate that you could make. What about quality? Well, in classical planning at least, maybe I'm slightly thinking, at least in the past few IPCs, people have been looking at minimizing the sum of discrete action costs. So you give each action a cost, and then you can define cost optimal planning, you can define a best quality plan that can be found within half an hour, things like that, based on the sum of these action costs. What can we do in temporal planning? Well, you could also minimize the cost. No surprise there, you could take any non-temporal planning cost heuristic, you could plug the LPGP action representation into it with the cost perhaps from the start of the action, and you could use that as your heuristic estimate of the cost. You could also minimize make spans for total plan execution time. Is this ever something we want to do? Well, in a sense we do, because we have these PDDL files which say column minimize make span at the bottom of them. Do we have realistic problems which require us to minimize make span? Sometimes we do, not always. Sometimes minimising meet span is actually a poor approximation to what it was we really wanted to do. If we're doing something like package delivery, then we might want to minimise our total late fees. So a plan which gets everything delivered, such that the last thing is delivered as early as possible, internally might be very suboptimal in terms of the individual goals, might be achieved at bad times. Or perhaps instead of the overall time, we actually really care about some per hour costs. We might care about fuel costs, and you can say, well, you minimise time, you minimise fuel costs, which is roughly true, but if we have different vehicles which have different fuel costs, then minimising time in one way might be more expensive than minimising time in the other. So there are various things we can do. Minimise make span has been the focus of temporal planning research for the past few years. A little bit of work that I did with Amanda and Jay last year in ICAPS started to look at this idea of time-dependent costs. So just to finish my half of the tutorial with some lies which I've told you so far. I have to complain about this. I'm just to touch on a little bit of other work. Now, the first lie is that the LPGP action compilation actually works per se works for most problems that most people ever want to solve. But one thing it doesn't allow you to do is to have an action to self-overlap. So we can't start an action A and then overlap with that another instance of A. In PDDL we can, but in the LPGP, essentially the representation it uses, we can't. You get some interesting consequences by allowing self-overlapping actions, one of which is that the complexity of temporal planning is X-space complete. So in theory the complexity is nasty. Most of the time, if people write a domain that allows self-overlapping actions, it's a bug. So for instance, if you have an action to load a package onto the truck, and you don't, at the start of the action, delete the fact that the package is at the location, you can then actually do some really weird things where you start another instance of that, and then in the middle the truck sets off and then the package is at two locations at once. It makes the search space horrible, and it will make temporal planners grind to a halt, whilst they try and find solutions that you didn't even think they could start to find. But the language does allow it, and it has some nasty complexity implications. The second thing is, putting these epsilon gaps in temporal planning is almost okay. They're saying we have this underlying sequential-like structure, and we're going to put epsilon gaps in. That's not strictly always possible with PDDL. So there's some interesting corner cases. For instance, if we start an action A at the same time as we start an action B, then it is quite legal for the start effects of action A to satisfy the overall conditions of action B, and for the start conditions of B to satisfy the overall conditions of action A. So essentially they satisfy each other's overall conditions. That's legal PDDL. It might seem a little bit mad, but it's legal PDDL, and it's broken by insisting on epsilon gaps. If we insist on an epsilon gap between A and B, then actually we can't, because if we insist on that epsilon gap, we've reached a state where the overall conditions of A aren't satisfied, because we strictly have to co-achieve them by simultaneously applying action B. So if you want to read Will Cushing's PhD thesis, it's covered in some detail there. So those are the two lies. Put these to one side, and today's tutorial has been a fairly complete and sound understanding of what's going on in sort of the basics of temporal planning. A few things we can do which make it a bit less onerous is, first of all, instead of building this total order where we put all these epsilon edges in, or zero edges, perhaps we're trying to avoid that, but actually in many cases we can leave out some of these sequence constraints. If two steps don't actually interact with each other, we don't have to commit to an ordering. We can build a partial order, still going forwards, but we can build a partial order. And it means in practice fewer of our STMs will actually fail because we haven't got all these needless ordering constraints in. So if B happened to be added to the plan after A, then we're not necessarily saying that B has to go inside A unless there's some interaction between them, in which case you do have to resolve it. But for many cases you can get rid of those edges altogether. And then the second thing which you can do with this basic representation, it follows on nicely from STPs, is an STP can be solved with an LP solver. Making an observation, you can then say, well, we can take the STP, We could also add numerics to that, so we can start to have numeric values that depend on time elapsed, for instance. And essentially bind those together and get continuous numeric processes by using some hybrid of the STP representation to give us constraints and actions, and an LP containing numeric constraints and the constraints and variables and some formula to work out their values to give us the kind of processes that are going on within that. So if you saw the tutorial this morning, you'll have seen some of this sort of thing already, and if not, then there is, as I mentioned at the start, there's a workshop tomorrow with some great work from there on continuing planning. And just to finish with thanks to the various papers I have referred to which made this tutorial possible.